Good morning, everyone. Today we will discuss an important topic in coordination chemistry, is the Chandelier theorem and its effects, type of Chandelier theorem, its consequences, and the problems, multiple choice questions associated with it. That is frequently asked in CSIR-NET examinations, GATE examinations, postgraduate entrance examinations, Jahn examinations, etc. So, this theorem was proposed in 1937 by Hermann Jahn and Edward Teller. They postulated that the theorem was all about instabilities of nonlinear molecular systems in electronic degenerate states and and its consequences. And this theorem was, or the statement of this theorem was revised by Hauscroft and Sharpe. And when we look into this, they are saying that Hermann Jahn and Edward Teller first said that instabilities of non-linear molecular systems in electronic degenerate state. What is this non-linear systems? We know the molecules can be classified as linear molecules and non-linear molecules, and this is applicable for systems which are non-linear, like the uh, octahedral systems we are taking, or the tetrahedral systems. Most probably, we are taking octahedral system here, and if these nonlinear systems are in a electronic degenerate states, they will be unstable and there are consequences. And what is this or electronic degenerate state means? There are two types of degeneracy we are learning. That is, the first one is the orbital degeneracy, which we are discussing in crystal field theory, that's associated with d orbitals. We know the 5d orbitals have the same energy in the spherical field, and if it is coming into the octahedral field, what will happen? The degeneracy is lifted, removed, or reduced. We say it will be either lifted, and it will be changing to T2G state and EG state. They will also have a triple E degenerate. They are also in a triple E degenerate or double E degenerate state. T means triple E degenerate and E means double E degenerate. And what is this electronic degeneracy? It is different from the orbital degeneracy. We will take an example of T2G1 and T2G3 case. So, electronic degeneracy, the case of T2G1, here we can see that the electrons are arranged in three different manners. First electron is in first orbital, second the first electron can be in the second, and the first electron can be in the third orbital. And both these three cases can have the same energy. And if this configuration is possible, we can say that this state is in an electronic degenerate state. They are electronically degenerate. You can say this is electronically degenerate. Here there are three different ways by which the single electron can occupy the T2G orbital. Here are three possible electronic configurations which have the same energy and electronic degeneracy is present. So this system is an example of electronic degenerate state. Please remember that. And when we consider T2G3 configuration, we can see there is only one way of arranging the three electrons in the T2G state. There is only one way by which the three electrons can occupy the T2G orbitals, and we can say it has no electronic degeneracy. Or we can say that this is a symmetrical system. The electrons are arranged in a symmetrical way, and here the electrons are arranged in a unsymmetrical manner. So unsymmetry means orbital degeneracy. Symmetry means there is no orbital degeneracy. And like this, if we are taking D5 configuration, we can see this is having a symmetrical arrangement, and there is only one way of arranging the 5 electrons, and this system does not possess an electronic degeneracy. So when we combine both the nonlinear systems and electronic degeneracy, as in the case of T1, these systems are unstable and they will undergo some kind of changes. That is the original statement of Chandelier, or the Chandelier theorem states that for a nonlinear molecular system in an electronically degenerate state will be unstable. So we have discussed what is nonlinear molecular systems, the systems like octahedral, and which are in electronic degenerate state like the T2, T2G1 or the T2G2 state. They will be unstable and will undergo distortion to form a system of lower symmetry, lower energy, and thereby removing the degeneracy. This is the statement for Chandelier. So it's important to know what is nonlinear molecular systems and what is the electronic degeneracy present. Are the configurations which we are given, they are they possessing electronic degeneracy or not? We have to find it out. So this Chandelier theorem or the Chandelier effect has two types of systems, that is Z in and Z out, and static and dynamic distortion. And when we look at the electronic degeneracy, we said that if the systems have electronic degeneracy, the electronic configurations will be unsymmetrical and they will show Jahn distortion. There is a distortion happening. The distortion in such a way that octahedral structure will change to distorted octahedron and point group will be changing to OH point group to D4H point group. And these systems show Chandelier. Systems like D1, we can see the 3 electrons can arrange in 3 different manners, or D2 configuration, the vacancy can be arranged here or here or here. It can be in 3 different ways. Or the D4 high spin configurations, electron can be here or here. So high spin D6 configuration, the paired electron can be occupying in the first orbital, second or third. Likewise, the D7 high spin, the unpaired electron can be here or here or here. And in D7, the electron can be here or here. It's a D7 low spin configuration. D4 low spin, the paired electron can be either in these orbitals. In the low spin D5, it can be here or here. In D9 configuration, this is D9 configuration. The paired electron can be here or here. So these arrangements or have electronic degeneracy, or they are unsymmetrical arrangements, and they show Chandelier distortion if the molecular system is in a nonlinear way. And the systems without electronic degeneracy, they are all symmetrical systems. That is, the electrons are arranged in a symmetrical way. You can see the 3 electrons in the T2G, 5 electrons arranged in the manner T2G3, EG2, D8 configuration. We can see T2G6, EG2, D10, that is the T2G6, EG4, and the low spin D6 configuration T2G6, EG0. They do not show Chandelier. This type of configuration does not show Chandelier because they are uh, arrangements without electronic degeneracy, and they are examples of symmetrical arrangements. So the symmetrical arrangement does not show electronic degeneracy and they does not show Chandelier distortion. The unsymmetrical, on the other hand, the unsymmetrical arrangement or the electronic degenerate arrangement or the systems with the electronic degeneracy show Chandelier distortion. And this is what is happening. The octahedral structure is changed to distorted octahedral structure, or the point group delta O is changed to D4H point group. The center of inversion which they possess will be removed. And these are some of the problems associated with it. The first question is, Chandelier effect is not observed in high spin complexes, or for example is given. First of all, we have to look into the questions once more. The question is, which configuration does not show high spin, Chandelier does not observe Chandelier in high spin complex? That is the question. And we have 4 complexes or 4 ions are given. We have to change these ions into the D terms first of all. This is example of D5. Cr2 plus is example for D4. Cu2 plus is example for D9. Fe2 plus is example for T6. So we have to look one by one. In D5 arrangement, we can see they are symmetrical arrangement. They five of them are arranged in five electrons are arranged in five orbitals. So they are symmetrical arrangement. They do not show electronic degeneracy, and we can say they do not show Chandelier effect. So the first is the answer, but we look into the other options also. In the case of T4 configuration, you can see uneven arrangement, and they will show electronic degeneracy. The electron can be here or here. In the D9 case, there is also uneven arrangement. There is a pair electron. There is unpaired electron here, and this one you can see the unpaired electron here. This can be here, either here. So this is an example of unsymmetrical arrangement, and they show electronic degeneracy. So these three states has are showing Chandelier distortion, and the first doesn't show Chandelier. The question was asked which does not observe Chandelier distortion, and it's option A. And the second option, Chandelier effect is not observed in high spin complex of here. The configuration is directly given. Just we have to write the configurations, the high spin configurations. First we will write D7 configuration. D7 is arranged in such a manner that there is possibilities for this unpaired electron to occupy these two orbitals, and three possible arrangements are shown, can be seen, and we can say they will show electronic degeneracy. So it is also having Chandelier distortion. The second one, D8 configuration. We have already said D8 configuration does not show Chandelier because they have a symmetrical arrangement. So there is no electronic degeneracy present, and no Chandelier is observed. D4 and D9 we have discussed in earlier question. So the answer is D8 is the answer. 2 is the answer. Either A, B, C will be asked, or 1, 2, 3, 4 is asked. A, B, C is commonly asked in CSIR or GATE examinations. Okay. Which metal complex is expected to subject to Chandelier distortion? Three metal complexes are given, especially low spin cobalt 2 plus that is having a D7 configuration. Remember, cobalt 2 plus means D7, chromium means D4, cobalt 3 plus means D6. Here, low spin cobalt 2 plus is asked, so low spin D7 configuration, it is arranged in this manner. And we can say Chandelier is present. In this configuration, there is Chandelier because both of the case there is the unsymmetrical arrangement and orbital degeneracy is present. Also in the case of titanium 2 plus. Titanium 2 plus means it is a D2 configuration. Remember, it is a D2 configuration, and the three arrangements are possible. So all of them will show Chandelier, and the correct answer is all. Fourth one, all of the above. This is in how we can deal with the questions that is involving Chandelier is there or not. And the second portion is in such a manner that Chandelier can be strong Chandelier. If a configuration is showing Chandelier, it can be either weak Chandelier or strong Chandelier. And the condition for strong Chandelier is distortion in EG orbital. If the EG orbital is unsymmetrically arranged, the EG orbital is unsymmetrically arranged, they will show strong Chandelier effect. Strong Chandelier effect or strong Chandelier distortion. And the only configurations showing strong Chandelier are high spin D4, D9, and low spin D7. You can see that here the T2G is symmetrically arranged, but the EG is unsymmetrically arranged. There's only one electron and one vacancy. Here we can see in D9 configuration, there is a paired electron here, there is an unpaired electron here. So we can say EG is unsymmetrically arranged. And in low spin D7 configuration, it is an electron in the EG, a vacancy in EG. That is unsymmetrically arranged EG. So unsymmetrically Symmetrical EG is showing strong Jahn-Teller. Remember that. And weak Jahn-Teller happens if T2G is unsymmetrical arranged. It is showing weak Jahn-Teller. The examples are D1, D2, D3, low spin D4. Here we can see low spin D4, low spin D5. Low spin D5 is there. High spin D6 is there, and high spin D7 is there. And these configurations show weak Jahn-Teller. So remember, strong Jahn-Teller is there, weak Jahn-Teller is there. And this is how we can distinguish the configurations into strong and weak Jahn-Tellers or non-Jahn-Teller. Here W is shown as weak Jahn-Teller, S is shown as strong Jahn-Teller, where EG orbitals is unevenly occupied or unsymmetrically occupied. N means no Jahn-Teller at all. First of all, we will see the configurations without Chandelier. We have set it that the symmetrical arrangement. If there is symmetrical arrangement, there will be no Chandelier distortions. So, if the case is D0, like D has no electrons, no D electrons are present, Chandelier will not be there. D3, no Chandelier. D8, there will be no Chandelier. D10, there will be no Chandelier. And also D6 low spin will be showing no Chandelier. And in the case of strong Chandelier, low spin D7 is having or is showing strong Chandelier. D9 configuration is showing strong Chandelier, and also high spin D4. Remember that in these cases, what is happening? The EG orbital is unevenly or unsymmetrically occupied. So this is how strong Chandelier and weak Chandelier can be found out. And these are some of the questions associated with it. Which of the following shows Chandelier distortion? This is similar to the earlier problems we had. High spin Fe3 plus is asked. We can draw high spin Fe3 plus in this manner. Fe3 plus means it is D5 configuration, and if it is a D5 high spin state, we will arrange in this manner, and we know this is unsymmetrical or symmetrical or even distribution, and this means there will be no electronic degeneracy and no Chandelier. And when it is coming to cobalt 2 plus, we have said that cobalt 2 plus means D7. If it is high spin D7, the electrons are arranged in this manner. 5 electrons are arranged in the 5 orbitals, and the 6 and 7 coming here. This configuration is showing Chandelier, and we need strong Chandelier. Remember, this is the one is having unsymmetrical arrangement in T2G. So weak Chandelier will be seen here. We have titanium 2 plus, which is a D2 configuration. D2 configurations, and the electrons are arranged in this manner. Here also the uneven arrangement is in T2G orbital. Last one, we have cobalt 2 plus. We know cobalt 2 plus is D7, but it is low spin cobalt 2 plus. And if we arrange the electrons, 7 electrons, we get these configurations, and these configurations we have an unsymmetrical or uneven distribution in EG orbital, and that means this is the one who is showing strong Chandelier, and the option is fourth option. This is showing strong Chandelier effect, okay, or strong Chandelier distortion. Again, another question is there. Strong Chandelier distortion is not observed for octahedral complex. It is given not observed. So we will look into the configurations. It is a D9. Copper 2 plus is a classical example of configurations showing or complex showing strong Chandelier, and that is D9 configuration, and it has a strong Chandelier. Then we will look into low spin chromium 2 plus. Chromium 2 plus means it is having a T4 configuration, and if it is low spin, the arrangement is the 3 electrons are arranged in the T2G, and the fourth will pair in the T2G itself. It is an example of weak Chandelier. Okay, and the other example of Mn3 plus. Mn3 plus is D4 Mn because it's Mn3 plus, and in the case of high spin, we can see the electrons is arranged in such a manner that we will get a strong Chandelier distortion. Also, we will look into the fourth option, high spin chromium. High spin chromium means it is also the same configuration, high spin T4. The arrangement is in this manner. So, copper 2 plus, high spin Mn3 plus, and high spin Cr3 plus, they are all showing strong Chandelier distortion, and the question was strong Chandelier distortion is not observed. So we will look into the weak Chandelier distortion, and it is given by low spin Cr2 plus, and option 2 is the correct answer. And which of the following D configurations show strong Chandelier from octahedral geometry? We know D1 is having a weak Chandelier. T2 is also having a weak Chandelier because the unsymmetrical arrangement is in T2G. And D9 is our answer because the unsymmetrical distribution is in EG orbital. T2G orbitals are symmetrically arranged, but EG orbitals are unsymmetrically arranged or unevenly arranged. So electronic degeneracy is present and strong Chandelier is possible in T9. The option is third one. And the other thing is that there are two types of distortions possible. Either we will say Z in or Z out, or static or dynamic. First of all, we will discuss the most important in one, that is the Z out distortion, which is the most commonly found distortion. So we will take copper 2 plus as a classical example. We know the copper 2 plus is a D9 system, and we arrange the electronic arrangement is in such a manner that T2G6 and EG3. And the first case we will take the two electrons are in dz square orbital, and one electron is in the dx square minus y square orbital, and the electronic configuration is in such a manner T2G6 dz square 2 and dx square minus y square 1 electron. This is drawn here. The EG is in such a manner. The two electrons are in dz square and one electron is in the dx square minus y square. Now what is happening is the two electrons, this is the z axis present, and this may be x and this may be y, and we know the dz square means this orbital in the z axis, and two electrons are present here. In the xy plane there is only one electron, that is we know x square minus y square is in the xy plane, there is only one electron. So in the case where both electrons are coming, this z axis will have the maximum repulsion, and the maximum repulsion, as a consequence of maximum repulsion because of the two electrons present, the z axis will get elongated here. Z axis is getting elongated, we can see, because of the repulsion and distortion due to the two electrons present here. There will be resulting in an elongation of the octahedron in the z axis, and this type of distortion is called as tetragonal distortion elongation. I will explain it to you. And because of the presence of two electrons, to lessen the repulsion, the z axis will get elongated. That means the ligand will be going further away from the metal orbital. So the axial bond, we can represent these bonds as axial bonds and equatorial bonds. The ligands which are in the xy plane are called the equatorial bond. The ligand in the z axis are called as axial bonds. Because of the presence of the two electrons in the z axis or z orbital in the metal side, the ligand will be further apart to lessen the repulsion. And because of it, there will be elongation in the z-axis, and this elongation is called as tetragonal distortion elongation. And another name for it is z out distortion, because z-axis is gaining length. It is called as z out distortion. Z is going in this side. Also, this distortion is called as 4 short bond 2 long bond distortion. 4 short bond 2 long bond distortion. That means the 4 bonds in the xy plane will be shorter, and the 2 bonds in the z axis will be longer. You can see A is greater than E. That means the axial bonds are greater than the equatorial bonds present here. And there are 3 names for Z out distortion. The names are tetragonal distortion elongation, Z out distortion, or 4 short bond 2 long bond distortion. And we can once more see what is happening here. The ligand in the Z axis is more repelled than the other 4 ligands in the xy plane due to the presence of the 2 electrons in the Z axis compared to the 1 electron in xy plane. And the repulsion and distortion result in elongation of the octahedron along with the Z axis, and this is called tetragonal distortion elongation. And here, because the Z axis bond length increases, it is also called Z out distortion or 4 short bond 2 long bond distortion. So 3 names are coming: Z out distortion, 4 short bond 2 long bond distortion, and the tetragonal distortion elongation. So remember this one. And when it is happening here, the energies of the d orbitals with z factors are lowered since the bonds along the z axis are elongated. We have said that to counter the repulsion, they are getting more lengthened, and because of the length is increasing or z axis is getting elongated, what is happening is the z factors orbitals d or orbitals with z factors are getting lesser energy, and the xy is getting higher energy because they are closer. Those ligands are closer to the or the orbitals are little more closer to the ligands. And this is most preferred distortion in and occurs in most of the cases, especially when the degeneracy occurs in EG level. So remember that if the degeneracy occurs in EG level, that means they have strong Chandelier distortion, and strong Chandelier distortion favors Z out or Z out type of distortion. And examples are D2, D4 high spin, D7 low spin, and D9 configurations show Z out distortion. And the distortion, there is a splitting of orbitals taking place. The T2G orbital is split into DXY, XZ and DYZ having the same energy, then DXY, then DZ square, and then DX square minus Y square. So remember the splitting in the DZ out in Z out distortion, XZ and YZ having the same energy, then dxy, then dx square, and dx square minus y square. And the second one is Z in distortion. We will also take the D9 system as an example. Here consider the 2 electrons are in the dx square minus y square, and 1 electron is in the dz square orbital. Earlier we had the 2 electrons in the dz square and 1 electron in the dx square minus y square. This was what happened in Z out distortion. The inverse is happening in Z in distortion. That's the arrangement is in such a manner: T2G6 dx square minus y square is having 2 electron, and dz square is having 1 electron. And as we can see, because of the 2 electrons present in the xy plane, this is the xy plane, the xy will be having more repulsion. Xy plane is having more repulsion than the z axis. So what is happening? The 4 ligands in the xy plane will be having more longer bonds than the ligands in the z-axis. So here the ligand in the xy axis is more repelled than the two ligands in z-axis. And the repulsion and distortion result in elongation of the octahedron along the xy axis. Here xy axis is getting elongated, and this type of distortion is called tetragonal distortion compression. Why it is called compression means the z axis is getting closer, and yeah, we are considering it with respect to the z axis. So this is called tetragonal distortion compression. And here, because of the bond length of xy axis increases and the bond length of z axis decreases. Here the bond length of z axis is decreasing, and because of the decrease in z axis bond length, we will call this distortion as z in distortion, or two short bond for long bond distortion. We can see the equatorial bond lengths are increasing. They are four equatorial bond lengths. They are increasing, and the two axial bond lengths in the z-axis are decreasing. For that, we are saying it is also called two short bonds, which represents the axial bonds in the z-axis, and four long bonds which represent the equatorial bonds in the xy plane. So three names are there: Z in, tetragonal distortion compression, and two short bond, four long bond distortion. And when it comes to stability, Z out is more stable because Z out has four short bonds and two long bonds compared to Z in, which is having only two short bond and four long bonds. These four long bonds are making Z in somewhat lesser stability than Z out. And when it comes to splitting, what is happening here is, here the energies of the orbitals with Z factors are increasing since the bonds along the Z axis are shortened. We know the axis is shortened, so the repulsion is more there, and the Z axis is having more. The factors which involve the Z axis will having the orbitals with the Z factors will have higher energy compared to the xy. This type of distortion is observed in cases of octahedral D1 configuration. The only electron will occupy the dxy orbitals with the lower energy. We can see that the dxy, then dxz, dyz, then dx square minus y square, and then we have the highest energy as the dz square. So remember the splitting. Dxy is having the lowest energy here, then dxz, dyz, then dx square minus y square, then dz square. And when we look into deep into this textbook, that is the Inorganic Chemistry Principles of Structure and Reactivity by James Hughey, we can see that the type of distortion can be arranged in such a manner that we can see D9 configurations, D7 high spin and low spin have Z out distortion, though not D out. This is all Z out distortions are there. Then D1 is having Z in, D2 is having Z out, high spin D4 is having Z out, and high spin, sorry, low spin D5 is having Z out distortion. So majority of them are showing Z out distortion, and that is depending on the configuration. All the strong Chandelier distortion, all the configuration which shows strong Chandelier is having Z out, and the other one are D2 and except D2 and D5. Okay, have a look into this. D1 Z in, D2 Z out, D4 high spin Z out, D4 low spin Z in, D5 low spin Z out, D6 high spin Z in, D7 high spin Z out, D7 low spin Z out, D9 Z out. And this is taken from James Hughey, Principles of Structure and Reactivity in Organic Chemistry text. And when we look into a CSIR-NET examination. This is the examination that I cleared. That is in December 2013 NET examination. And the question is two compounds are given, A and B, K2BaCu NO2 6 times and CS2BaCu NO2 6 times. These two compounds are showing Chandelier distortion. And which type of Chandelier distortion? The complex A is showing tetragonal elongation. Tetragonal elongation means that is Z out distortion, and tetragonal compression means that is complex B is showing Z in distortion. And the unpaired electron in A and B are found respectively in orbitals, and four orbitals are given. First is the dz square, and second one dx square minus y square. That means A, the unpaired electron is A in dz square, and B is dx square minus y square. And this is in such a manner they are asked. We have to find out where the unpaired electron of A and B are present, in which orbital it is present. So we have, first of all, we have to look into the configurations, what the copper oxidation state of copper is and which configuration it is. So we know potassium has a +1 charge, so there are two potassium. Barium has a +2 charge. Copper we don't know, and NO, when it comes to NO, it has a -1 charge. So +2 +2 plus X minus, here 6 ligands are there, so -6 equal to 0 is the arrangement, is the equation. +4 plus X minus 6 equal to 0, and we will get X minus 2 equal to 0 and X equal to -2, which you all know. So the copper is in its +2 electronic, so +2 oxidation state, and that is an example for D9. We know the first A is a D9 system, and B, when it comes to B, it is the same method, because cesium has having a +1 charge and the barium has having a +2 charge. So the same equation we will get copper +2, that is also a D9 system. So what we have to do is just arrange the electron in this manner. So we can see the figure here. In the first, we will look into tetragonal elongation, Z out, and we will arrange the 9 electrons, and we will, if we arrange the 9 electron, 4 electrons in dxz dyz, then 2 electrons in dxy, total 6 electrons are there in the eg. And when it comes to T2g, when it comes to eg, 3 plus 2 electron, total 9 electron, and the last electron is in dx square minus y square. So in the complex A, the unpaired electron is in the dx square minus y square orbital, and in complex B, the last electron, if we arrange dxy, dxz, dyz, dx square minus y square, and dz square, because it is an example of tetragonal compressed complex, and it shows that in distortion. And if we arrange the last unpaired electron, or the unpaired electron is in the dz square orbital, so we can say for A, the unpaired electron is in dx square minus y square, is because the z out, and for B it is z in, so the last electron or the last unpaired electron will be in d z square orbital. This is A and this is B, and this is the correct answer here. And if you have been asked that A exhibit tetragonal compression and B exhibit tetragonal elongation, this will be the answer. A and B will be the answer. The A will be the answer, but here If A is tetragonal elongation and B is tetragonal compression, then the unpaired electron of A and B are found respectively in the orbitals of dx square minus y square and dz square. So you have to learn the splitting of dz out, z out and z in thoroughly, so that you can answer this question smoothly. The questions related to this type are asked in all the examinations, all the competitive examinations. So the second problem, four complexes are given: NiH2O6 times 2 plus, MnH2O6 times 2 plus, CrH2O6 times 2 plus, and DiH2O6 times 3 plus. The ideal octahedral geometry is not observed in. That is what is asked. And for ideal octahedral geometry, what we will have, the pre-requirement is there should be no Chandelier distortion. If Chandelier distortion is taking place, there will be no ideal octahedral geometry present. So we have to look whether these complexes show Chandelier. We know nickel 2 plus is an example of D8 configuration, Mn is an example of D5, and Cr 3 plus is an example of D3. But we know in the spectrochemical series, H2O is a weak field ligand, so it is high spin state. These three complexes are in high spin state, and the fourth one is having a D1 electronic configurations. And we know high spin D8 configuration, high spin D5 configuration, and high spin D3 configuration. They do not show Chandelier distortion because of their symmetrical or even arrangement, and there will be no electronic degeneracy present. The only case with Chandelier is, even if it is a weak Chandelier, titanium H2O 6 times 3 plus is the correct answer, because it is showing Chandelier, and octahedral geometry is changed to distorted octahedral geometry, distorted OH geometry. And the correct answer is D is the correct answer, and the only option that carries is D only, and the D is the correct answer. And the other statement, other questions, the correct statement about CuN bond distance. CuN bond distance is asked. Cu NH3 6 times 2 plus is, are they are all having equal bond distance, or axial bonds are longer than equatorial bonds, or equatorial bonds longer than axial. And the other question is all bond distance are unequal. So we know it is having, the copper 2 plus is having a D9 configuration. It is showing strong Chandelier distortion, and the strong Chandelier means there will be no ideal octahedral geometry observed, and it is having a distorted octahedral. So if it was a perfect octahedral, we can say that all bond lengths will be equal, and this is not in this case. Copper is having strong Chandelier. So the first option is not right, and the second and third we will look into this, and the fourth we can also say that it is also wrong, because all the bond distances are unequal. We know, we have seen earlier that there is the axial bonds and the equatorial bonds. Axial bonds are, two of them are axial bonds and four of them are equatorial bonds. These four of them have having the same bond length, and these two also having the same bond length. So this is also not right, because it is said that all bond distances are unequal. That is not in the case. There is only two different arrangements. Either they can be axial bond distance or they can be equatorial bond distance. And the next question is, what about the axial bonds are longer than equatorial bonds, or equatorial bonds are longer than axial bonds? Uh, Also, we have to look into that, which type of arrangement or which type of distortion is shown here. We know that D9 system has an Z out type of distortion. And when it comes to Z out, what is happening is the two Z axes are getting longer. Two Z axis or bonds in the Z axis, metal ligand bond lengths in the Z axis are getting longer, and they are represented as axial bonds. So we can say that two axial bonds are longer than the four equatorial bonds. We know it is also called two long bond, four short bond distortion. So the case is that the axial bonds are longer than equatorial bond is option B, and the option C is the equatorial bonds are longer than axial bonds. So we can go with the option B because it is a Z out distortion, and in Z out what is happening is axial bonds are longer than the four equatorial bonds. Remember the axial difference between the axial and equatorial bonds in Z out and Z in. And the last question. So option B is the correct answer here. For the complex ion Cu NH3 6 times 3 plus the octahedral geometry will be as octahedron. This has tetragonally distorted octahedron or trigonal prismatic or trigonal anti-prismatic. We can avoid both these structures. Both these structures can be avoided. Either if it is showing Chandelier, they will be tetragonally distorted Chandelier of, or if it's not showing Chandelier, it will be an octahedral, purely octahedral structure because of the six ligands present. So when we look into the complex, the tricky part is it is a plus 3 complex. Plus 3 means if it is a D9 system, we can say that it shows strong Chandelier and the structure will be tetragonally distorted octahedron. But here the Cu is in its plus 3 oxidation state. That means that the electronic configuration is D8 configuration, and D8 configuration means it shows no Chandelier distortion, and no Chandelier distortion means it has a structure of octahedral structure. It has a pure octahedral structure, and we will go for option A. Option A is the correct answer here. And the next type of Chandelier distortion is a static one and the dynamic one. And the static Chandelier distortion means complexes having measurable bond length differences are examples of static Chandelier distortions. You know the word meaning static, and what is meant by dynamic. Dynamic means moving, static means which is stable or which is staying idle. Some molecules show tetragonal shape under all conditions, that is, in solid state or in solution state at lower or relatively higher temperatures. This is preferred to be static Chandelier distortion, and it is observed in degeneracy, where the degeneracy is in EG orbitals. Hence, the distortion is strong and permanent. We know that if the degeneracy is in EG state, the Chandelier distortion will be stronger, and for static it will be permanent in a permanent manner. Here we can have measurable bond length differences in this type of distortion. And when it comes to dynamic Chandelier distortion, in some molecule, the distortion is not seen either due to random movements of bonds, which do not allow the measurement within a time frame, or else the distortion is so weak as to be negligible. And when it comes to dynamic Chandelier distortion, we cannot measure the bond differences. There is actual bond differences, but because of the random movements of the bonds, what is happening is we cannot differentiate the bond length differences here. However, the distortion can be seen by freezing the molecule to lower temperature. So if we want to view it, we have to freeze it in low temperatures, so that the random movements will be stopped at lower temperature, and bond difference will be correctly measured. This condition is referred to as the dynamic Chandelier distortion, and here the complex oscillate among three equivalent tetragonal structures. That is what is happening. The complex is oscillating between three equivalent tetragonal structures, and all the bond lengths are randomly moving, and which is making us hard for making exact measurements. And the examples are Mn2 PbCu H2O 6 times, where M can be Kb, Rb, Cs, and Ta. And the complex This is a classical example for a complex having Chandelier distortion. FeH2O 6 times 2 plus. So Chandelier distortion and appears octahedron. And in this case, the distortion is small since the degeneracy occurs in the T2G state. Also, there can be possibilities for a weak Chandelier also. Here, the complex show Chandelier distortion, but it is a dynamic one, and when we measure, all the bond distance are same as in a pure octahedron. But if we are freezing it, we can see the bond difference between these ligands or the orbitals. And the next one is CuNH2 6 times 4 minus exhibit full range of static and dynamic Chandelier. It's another example where we can see static, both the static and dynamic Chandelier effects. The example is CuNO2 6 times 4 minus. Okay, and another question regarding this dynamic Chandelier complex which shows dynamic Chandelier is the DD absorption band of FeH2O 6 times is split due to presence of octahedral geometry, static Chandelier, dynamic Chandelier, or presence of tetragonal bipyramidal geometry. We said that FeH2O 6 times 2 plus is an example of dynamic Chandelier distortion, and the absorption spectrum, the absorption band is split. That is a consequence of Chandelier, and that is because of the dynamic Chandelier distortion. So C is the correct answer here. Remember this complex, which is a classic example that we discussed for dynamic Chandelier distortion. And these are some of the consequences relating to Chandelier distortion. The first one is six coordinated complexes are found to possess distorted octahedral structure due to this effect. As we have mentioned, the pure octahedral structure is changing to distorted octahedral structure due to this effect, and the absorption spectra of the complexes having this distortion are different from the other spectra. There is a shoulder which appears in the presence of Chandelier distortion. So absorption spectra is changing if there is a presence of Chandelier distortion. Its shoulder is appearing here. And the third one, due to Chandelier distortion, the point group of OH point group is changing to D4H point group, which we have already mentioned, and because it is because the OH loses its center of symmetry. We know in OH point group there will be an I, and when it comes to Chandelier, the pure octahedral structure will loses its forms and it is changed to distorted octahedral, where the center of symmetry of the structure is lost. And the fourth one is, even though Cu En3 thrice 2 plus contains 3 chelate rings, it is less stable than CuEn twice H2O times 2 plus, which contains 2 chelate rings. When we studied the stability of the complexes, we have learned that chelate rings, those complexes which having more chelate rings are stable than the its counterpart having lesser chelate rings. Here, when we take complexes which having 3 chelate rings and a complex which having 2 chelate rings, because of Chandelier, the complex which having two chelate rings is stable. You can see, you can understand from the figure. This is an example for figure for CuEn thrice 2 plus, and this is CuEn twice H2O twice. We can see that because of the Z out distortion, what is happening is these rings are under tremendous strain, and because of the strain imposed by Chandelier distortion, or especially the Z out distortion, this complex will be unstable. And when it comes to the complex containing two chelate rings, there will be no strain because in the Z axis H2O ligands are present, and just the H2O ligands will have a longer bond length, and there will be no strain installed into the chelate rings, so that we can say that this complex will be stable than the complex with the three chelate rings. And another one is coordinately labile nature of CrH2O 6 times 2 plus and COH2O 6 times 2 plus. We know the what is meant by labile and inert complexes, and CrH2O 6 times 2 plus undergo substitution easily because of the D4 system, because it is a high spin D4 system. And what is happening in the high spin D4 is that they will show strong Jahn-Teller distortion. And because of the strong Jahn-Teller distortion, the complex which is having or the ligand, the H2O ligand in the Z axis, there will be a Z out distortion. Z out will be there. So the H2Os in the Z axis can be easily substituted, and this hydrated Cr2 ion is coordinately labeled. We can say that it is coordinately labeled due to strong Jahn-Teller distortion. And the case of CONH3 6 times 2 plus, here water molecules can, as the above case, we can explain this thing. It is a octahedral D7 system. It is a D7 high spin system because of the D7 system, or because of the Jahn-Teller, sorry, not high spin, low spin system. And it is also showing Z out distortion. Because of the Z out distortion, because of the strong Jahn-Teller, what is happening is the NH3s in the Z axis can be easily substituted by another ligand, and this is also a consequence of Chandelier, both in the case of CrH2O 6 times 2 plus and CONH3 6 times 2 plus. Their labile nature can be explained by Chandelier distortion. And this is what is we are observing in the spectroscopic observations. The Chandelier distortion can be observed using a variety of spectroscopic techniques. In UV visible observation spectroscopy, distortion causes splitting of bands in the spectrum due to a reduction of symmetry. We know that the OH system is reduced to D4H symmetry, and because of it, a splitting of band is observed. This is an example for the octahedral, purely octahedral distortion, and when we are taking UV wavelength versus absorbance, we can see a band, single band here. And when it comes to D4H point group, when it is changed to D4H point group, the UV band will have a additional shoulder there. And consider the hypothetical case of OH symmetry showing a single absorption band. If the molecule uh, is undergoing Chandelier distortion, the number of bands will be increasing by 2. There will be a single band in pure octahedron, and there will be a double band in D4H point group, which shows Chandelier distortion. And the question arising from this portion is that the absorption spectra of TiH2O 6 times 3 plus in solution comprises of a maximum of a shoulder, and the reason is LMCT, that is the ligand to metal charge transfer, MLCT, that is the metal to ligand charge transfer, Chandelier distortion, or nephrocytic effect. We know that it is the shoulder is because of the Chandelier distortion. First of all, we have to look into the complex for that. If the complex is showing Chandelier or not, titanium 3 plus is D1 configuration. We know D1 configurations is having Chandelier distortion, and this is because of the Chandelier distortion they are having shoulder. So option C is the correct answer. And these are another examples. We can, when we look into COH2 6 times 2 plus, where this complex is not showing Chandelier, and if the complex is showing Chandelier, what are the difference? We have discussed Cu2 plus is a classical example of Z out Chandelier distortion, and because Z out is coming, the two axial bonds in the Z axis are getting longer. That means they are having a longer bond length than the equatorial bonds. 4 equatorial bonds present here in the XY plane. We can see a 0.45 Armstrong difference in bond length here. If there is no Chandelier, all the bond lengths will be equal. That is another consequence. And a classical example of copper hexafluoride. Copper hexafluoride also has showing a Chandelier, that is a Z out distortion is shown here. we can see that the fluorines in the z-axis, fluorine copper bond length in z-axis is more than the copper fluorine bond length in the xy plane, and that is also because of Chandelier distortion. You can see a 227 picometer and 193 picometer, and this is in the z axis. Bond length in the z axis is longer because of the z out distortion than the xy plane. And these are all examples for this. Thank you for listening.